Yep.
Okay, welcome everyone to here today. So it's the second talk of this series. And today we are very kindly to invite Professor Bill Smith. Bill Smith. I will say he is the kind of the father of hyperspectral infrared sounder in orbit. And he published more than, I would say, 100 of publications all the whole his career in his career and including the use of satellite sounder data and how to handle that, and also doing that using that for applications. Not only this, he also serve a lot of community-related work and help to educate students. Our former Vice President, Professor Zhenglong Liu, also his students before when he studied in Wisconsin. I also studied in Wisconsin. By that time, Bill is in Langley, not much time in Wisconsin. But Professor Zhenglong Liu, he is one of Bill Smith's students. So you will know that we are third and fourth generation right now. He received numerous awards from NASA, from NOAA, and including AMS Fellow, American Meteorology Society Fellow. That's a very outstanding award, and so that's what he can share all what he has been done before. Okay, so that's a kind of brief bio for Bill Smith. So now he will share some of his experience in hyperspectral infrared sounder. All right, Bill.
Okay.
Okay.
Okay. 谢谢. Ni hao. It is a pleasure for me to be with you this morning in Taiwan to discuss the evolution of hyperspectral sounding, atmospheric soundings from satellites. And before we start, I'm showing this picture of the NIMBUS satellite. It's NIMBUS 3, which was launched in 1969. I was there. I was working on the, yeah, I'm an old man. I was working on these first instruments, the first atmospheric sounding instruments, which flew into space on this NIMBUS satellite in 1969. And this satellite carried two spectrometers. One spectrometer was called the IRIS, the Infrared Interferometer Spectrometer. And this was what's called, and you're going to hear more about this in the lecture, this was a Fourier transform spectrometer. This spectrometer measured a large portion of the infrared spectrum with a single detector. But a Fourier transform spectrometer can measure many, many spectral channels, the spectrum here, with one detector. So that was one instrument that flew. The other instrument which flew is the satellite infrared spectrometer. Oh, I don't know, something happening here. That was called Sears A. And the Sears A instrument had 8 detectors to measure 8 different spectral channels. And you can see them numbered here, 1, 2, 3, 4, 5, 6, 7, and 8. And this is the carbon dioxide absorption band. And measurements near the strongest absorbing region of this band looked at the high levels of the atmosphere. These are the atmospheric layers from which the radiation to space was coming from. So this is the 1, 2, 3, up to channel 8, showing how as you go from the very absorbing part of the band, where the emission only from high levels gets to space, to the less absorbing region of the band, where the energy from low levels can escape to space, then the signal comes from lower and lower altitudes of the atmosphere. And this, of course, is the way you sound the atmosphere, is by making measurements at different spectral channels, which gives you radiation from different layers of the atmosphere. So these were the first two instruments, and they were successful. They were quite good in that the radiance measurements were very accurate and so on. And some improvement in forecasting took place, but not as much as we had hoped. And the reason we didn't get much improvement in forecasts with these data was because they had very poor vertical resolution. And that's shown here on this diagram, which shows a comparison between, and possibly some of you people who have worked with these data, the TOVS, the Tyros Operational Vertical Sounder, which had about 20 spectral channels, but the sounding from that device is very smooth. Whereas if you compare that to a radiosonde that was launched beneath the satellite, you see much more structure. And this is because the vertical resolution of the satellite is very coarse. Those weighting functions are very, very broad, as you saw in the previous figure. And so the satellite was not able to resolve fine scale vertical features such as the tropopause region, as shown here, or frontal inversions. This is an inversion, a frontal inversion, and you can see the satellite can't resolve that. It just smooths right through it. Or the low level boundary layer inversion, which you see here, not resolved by the satellite sounding. It only gave you sort of a vertical mean profile of the atmosphere. Whereas for weather prediction, especially storm prediction and so on, we need these very fine vertical details of the atmosphere. And this is why we then decided to develop something that would give us much higher vertical resolution, which we call the hyperspectral sounder. And the hyperspectral sounder was developed to provide very high vertical resolution, as we'll see in a moment. And we'll see why it can do that. It actually began in 1977, right after I moved a group of mine from Washington to Madison to where I then became a professor. And of course, Professor Liu, who was one of my students there in these early days. But at that time, I was looking for a way to get much higher vertical resolution. And a person by the name of Tom Kyle came and talked to me about an idea that he had about using an interferometer, or what's a Fourier transform spectrometer, rather than a low resolution spectrometer or filter radiometer like the TOVS was. And so we then developed what we call an interferometric method to sound the atmosphere in the late 70s. And what we saw was that whereas spectral radiance, like was measured from the NIMBUS satellite in the beginning, the radiance, if you measure radiance directly, it's emission from a deep layer of the atmosphere, as we saw from those weighting functions. And whereas if you look at the interferogram, the Fourier transform of the spectrum, you will see resonance regions, which the amplitude of the signal is a function of the vertical structure within the atmospheric layer. It's not just the layer mean temperature like the radiance is, but the interferometric signal gives you the structure. If you have no structure, if the temperature isn't changing with altitude, this signal goes to zero right here. Whereas if you have sharp lapse rates or so on, then you get this resonance region. And that's if you have high spectral resolution where you can resolve individual carbon dioxide emission lines, in this case, for atmospheric temperature. And at that time, in this paper, we showed that if you retrieved atmospheric soundings from these data, you would get a temperature accuracy which was almost twice as good as we could get from the lower resolution data. We went from like 2 to 3 degrees to like 1 to 1.5 degrees in terms of atmospheric temperature. So once we found this from theoretical simulations, I presented this to NASA in Washington and NOAA. At that time, it wasn't called NOAA then, it was called ESA, I think. But in any event, and nobody quite believed it. They said, oh, you can't get that kind of high vertical resolution from space, that we don't believe you. And I said, well, I'll prove it. If you give me the money to prove it, we'll build an aircraft instrument and fly it on a high altitude aircraft, and I'll demonstrate that we can get high resolution soundings. So NASA and NOAA jointly provided money for us at Wisconsin now to build an instrument which we called the High Resolution Interferometer Sounder, or HIS. And we built this instrument in the early 1980s, and this is the instrument here. It actually, this is the NASA ER2. It's a very high altitude aircraft that flies at 20 kilometers, almost in space. In fact, the pilots wear space suits because they're so high. There's no oxygen at all. And they have to wear space suits flying at that level. And in any event, we built an instrument that flew right on the underbelly, the underside of this aircraft, and looked down at the atmosphere from 20 kilometers to simulate what we would get from a satellite. And you can see here, this is the instrument, the HIS instrument in the underbelly of that aircraft. And whereas these previous spectrometers and radiometers and so on that we were flying would only observe, 20 or at most 25 spectral channels, this instrument observed many thousands of spectral channels. You can see them all here. This is the spectrum, CO2 emission. This is the window region, the ozone band emission, and all these trace gases you could see with these spectra. And you can see from all these wiggles, this is not noise. These are all signals from these gases. And there's thousands. I think we had like 6,000 different spectral channel measurements with this instrument. And it's having all those channels, as we'll see, that gives you the high vertical resolution. And so we built this instrument and we flew it in 1986, and we flew it over the ocean just off the coast of southern Florida. And we then observed the vertical structure of the atmosphere as the plane flew along. This is just a small track portion of the flight track. This is 75 kilometers wide. And this is the water vapor retrieval, the humidity that we retrieved from those thousands of spectral radiance channels that were observed with this interferometer. And you can see very high vertical detail in this water vapor structure. The red is high humidity, and the blue is very low humidity, as you can see here. So, and then we had a radiosonde launch right about midway through this flight. So this is a balloon measurement, a radiosonde measurement that was taken to validate the structure we were seeing with our aircraft instrument. And you can see all this detail in these data, a lot of detail, more detail than you see in the radiosonde really, but you can see the moist boundary layer here, and you see that in the radiosonde. Then it gets drier, and you can see that here in the radiosonde. Then it gets wetter again. This red layer here. And then there's a deep dry layer through the middle to upper troposphere. That's this blue area. And then we get up into the high altitude near the tropopause, and of course where cirrus clouds and so on tend to exist as well. And we see it gets moist again. And you can see that moisture right here from the satellite, from the aircraft experiment. And so after the NASA and NOAA people saw these results, then they said, well, we need to fly one of these instruments, which they then planned to do on Polar Orbiter first. We actually had wanted this to go on geostationary satellites so that we could use this high vertical resolution structure to improve nowcasting and severe storm forecasting and so on. In any event, you might ask the question, well, how does this concept work? Why does having thousands of channels like we had give you high vertical resolution? And I want to explain that now. It's due to what we call Shannon sampling theory. It's Shannon sampling which enables high vertical resolution with hyperspectral measurements. And the concept was developed by Claude Shannon back in 1948, actually, long before we were even thinking about hyperspectral sounding. And what he showed is that if you keep repeating a signal, it will amplify, and the noise in the signal will cancel because it's random. But the signal itself, like your voice or a message that's being sent through a cable across the ocean or something like that, will amplify. And so he developed this theory for communication. But the Shannon theory applied to all kinds of things. For example, it applies to imagery. If you have an image, just one image, for example, you may not see an object in it because of the noise of all the surrounding pixels. You can't see the object that you're looking for in the image. But if you take another image and another image, and you keep adding them all together, the noise, the signal will enhance. You keep building up the signal from the object, whereas the noise doesn't change. It's just random noise. So after you add enough signal images together, you'll start to see the object, and you'll be able to determine what the object is. You'll be able to identify it. And this is the same concept that's used in space exploration, or exploration of our galaxies with the Space Telescope. We just dwell for a long time, making lots and lots and lots of images, adding them together. And in this way, we can see things that you cannot see in a single sample or even in a small time period. But if you dwell for a long time, you'll be able to see things that you otherwise couldn't see, like distant planets and galaxies and things of that nature. Well, it's the same thing with hyperspectral sounding. In a single measurement, if you look over here on the right, these are these weighting functions. In a single measurement, you can identify a high vertical resolution feature, such as the tropopause or a frontal inversion or anything like that with a single measurement, because it's very low resolution. But if you take thousands of measurements, as you keep adding more and more spectral data together, you'll start to resolve these fine scale vertical features, because the signal will keep amplifying from all these measurements. An inversion like the tropopause is seen in many, many, many measurements, and that will be amplified. So this is how Shannon sampling enables hyperspectral sounding to get high resolution. And this is why hyperspectral sounding instruments like the CRIS and the IAZI and so on, or the Chinese high-res instrument is another example, or the gear instrument, which is on geostationary orbit. This is why they have thousands of spectral channels, is so you can get high vertical resolution. So that's important to understand how that works. And so if you just look at the multispectral instruments like we used to fly, there's a very small number of measurements or vertical weighting functions, whereas the hyperspectral instruments have thousands of spectral measurements. And having those thousands of spectral measurements translates into very high vertical resolution then, compared to a multispectral, low spectral resolution instrument. So the vertical resolution ratio between hyperspectral and multispectral ranges between 3 and 6, depending on the level. The lower you are, the greater the power of hyperspectral measurements. And that's good because we need to resolve the boundary layer and so on. In any event, these are the polar satellite hyperspectral instruments, some of them that are flying in space today. The AIRS was the first one. It was not an FTS. It actually was like the Sears A. It had a separate detector for every spectral channel, but it used a very large focal plane detector array, so it still was able to get a spectrum like an interferometer does, but it's a bit noisy because of the separate detectors for different spectral channels. This is the noise level of these instruments. The AIRS is blue. The IAZI is the red. That flies on the MEDOP satellite. There's 3 of them in orbit right now, and that started flying in 2006. And the lowest noise instrument, and you'll also notice the very smallest instrument, is called the CRIS instrument. And actually, China has an instrument just like CRIS, which they call high-res. And it's a copy of CRIS, really, the CRIS design. But, and it's on the FY3 satellite. In any event, the CRIS, and as well as the high-res, they're very small instruments. And the CRIS is the smallest and most accurate of all the polar hyperspectral sounders. You can see it's the smallest by just looking at the these pictures here. And you can also see from the noise curves here that it has the lowest noise of all the hyperspectral instruments in all, even at long wavelength all the way to short wavelengths. So then the real original objective for hyperspectral sounding, as I said earlier, was to fly it on a geostationary satellite so that we could get use the data for storm prediction. And so in 1999, I left Wisconsin, or 1997 actually, I left Wisconsin for a short period of time, at least I thought it would be a short period of time, to get NASA to fly a geostationary imaging Fourier transform spectrometer. This instrument used a very large detector array so it could look at a volume of atmosphere, thousands of kilometers on a side at one time with many detector elements. And it was actually able to obtain about 80,000 atmospheric soundings per minute. And it had very high resolution, 4-kilometer resolution. We built this instrument and we tested it on the ground, but unfortunately, it never got into orbit because NASA's budget was cut, or actually the president told NASA they had to go to Moon and Mars rather than spend their money on this. So it never got into space. But the good news is that both Europe and China copied the GIFS design, and they started building the instrument. And the China was the first to launch the GIFS-like instrument on FY4A in 2016. They call this the GEARS instrument. And the GEO stationary interferometric infrared sounder, or GIRS, but it's GIFS-like. It's just like GIFS spectrally. And it also, the only thing different than GIFS is that it has 16-kilometer spatial resolution rather than 4 kilometers. And this is more like the polar satellite spatial resolution. But China's going to launch 2 more of these instruments, and each one will have higher spatial resolution, and the third one that gets launched will be like the full GIFS capability. And also, Europe is going to fly the same type of instrument. It's more like GIFS. It's 4-kilometer resolution, same spectral bands and so on. They're going to fly this in 2 years now. They're launching it in 2023 on their Meteosat 3rd generation satellite. So GIFS now is getting into space. One is already in space and another one is coming soon. And the US has also started now finally building one that will be over the Americans, which they plan to launch before the turn of the decade, 2030, before that time. Well, anyways, in the United States, we didn't have our geo-hyperspectral instruments, so I started working with the group to use the existing data that we did have to simulate geo-hyperspectral soundings. And the idea here was to make use of the polar orbiting hyperspectral instruments, which we had many in orbit. We have, I think, 8 of them in orbit now on polar satellites. So they're fairly frequent when they come over every few hours or so. But their spatial resolution is kind of poor. It's like 15 kilometers rather than the 4 kilometers that we want. But to combine that with geo imagery soundings, which are very high spatial resolution. They're on the US, the ABI instrument, which you heard about the other day from Tim Schmidt. He told you all about the ABI. That's very high spatial resolution, and it's very high time resolution. As high a resolution as 5 minutes. So the idea was to combine data from these 2 instruments, direct broadcast data, which is real-time data gotten from the polar orbiters. And of course, we get real-time data from the geostationary imagers, is to combine these 2 data together to simulate high spatial, high vertical, and high temporal resolution sounding, similar to what you would get from a geo-hyperspectral sounder. It's not real geo-hyperspectral because we're putting these things together. It's hyperspectral at the LEO or the polar satellite resolution, but it has the time and space resolution of the geo imager. And so we've done this for several years now, and we run a system operationally 24 hours a day, 7 days a week, and where we use direct broadcast data gotten from the United States, readout station, both at the University of Wisconsin and at the Hampton University, where I am now in Virginia, and also from Miami. We get good coverage of the continental U.S. from those 3 direct broadcast systems, and so we take that polar data and we combine it with the ABI data, which covers that same region, and we produce these simulated geo-hyperspectral soundings. So we combine, for example, the polar sounders METOP, the IAZI, with the JPSS, the CRIS instrument, and we combine that with the GOES ABI. Or we've done this over Asia too, where we've combined these polar orbiting data with the Himawari AHI, which is an instrument almost to the ABI, and this taking over itself. I don't know why it's doing that. But. Oh, sorry. In any event, and with the we could use the high res also on the FY3D, and we can also use the GEARS instrument, combine these data because it's also low spatial resolution, 16 kilometers, with 2 kilometer resolution AHI data, and get similar high resolution geostationary soundings. And this is all explained in this reference here, which if you're interested, you can read about that. It's in a paper, a JTech paper. But as I said before, the idea is to combine data from the low vertical resolution geostationary imager systems like ABI, but they have very high horizontal resolution and time resolution. Combine that with the polar hyperspectral instruments, which have high vertical resolution, but very low horizontal and low time resolution. And the end product then is high spatial and high time resolution, hyperspectral vertical resolution soundings. And this just shows an example of it over where I live, Virginia. I live right here, actually. This is the state of Virginia. This is the Atlantic Ocean over here. Anyways, this was a pass over this area that we received at Hampton University, which is right here. And this is the data from the polar satellite. You can see it's low resolution. And then we combine that with the geostationary data, which is high resolution, and we get this product. This is 500 millibar temperature, or 850 millibar temperature, and this is humidity down here. And you can see how the combination gives you high spatial resolution and even fills in gaps in the data. For example, here beyond the edge of scan and in between cloud elements that aren't resolved with the polar data, but the high resolution geostationary data gives you information in between clouds and so on. So it fills in cloud gaps like these in here in the polar data. And if you compare it with conventional data, conventional radiosonde analyses like the RAP model provides, you can see it's in fairly good correspondence with conventional data. So we use these data and we put them in a forecast model, and we assimilate these hourly. We don't use 5-minute geostationary data, but we do produce the soundings every hour over a large region, over the continental US and the surrounding ocean regions. And we assimilate these data hourly, continuously, to produce initial conditions from which we can then produce forecasts. And we do forecasts of course, the atmospheric state parameters, plus where storms are going to develop. We even use it for tropical storm prediction and so on. And the whole idea is to show how these data can improve weather forecasts. And the first thing we found was that these data improved greatly by assimilating temperature and moisture, especially moisture, largely moisture, assimilated continuously with high resolution, like 2-kilometer resolution, which we get from the ABI. The model will be forced to produce an accurate wind field. The model dynamics is forced by the thermodynamic observations to produce accurate winds. And that's very important. And that's shown here. For the whole month of June, I'll show you the wind vector error. This is from 3 hours of assimilating data compared to radiosonde data. And this is the error. It's only like 2 meters per second. Now, less than 2 meters, 1 meter per second or so, when you assimilate the satellite data compared to what the model produces if you don't include the satellite soundings, which is 2 or 3 times poorer than using the satellite data. And then we even compared this with cloud drift winds, where you track moisture and cloud motions to get the wind profile. That's the green curve. And it's better than the control forecast, but not near as good as the satellite sounding assimilated forecast. And so it's this dynamics that get forced by by assimilating the temperature and water vapor soundings that will improve forecasts. And so this is also when you have high temporal resolution sounding data with high spatial resolution, you'll get the wind field, three-dimensional wind field. You don't need to track clouds and water vapor and so on. This will come from the model. It's forced by these thermodynamic data. And this will produce better forecasts, as shown here. These are just 6-hour forecasts. The blue is the control without satellite data, and the red is with satellite data. And you see that the temperature, the humidity, and the wind field are greatly improved by assimilating these data. So we've been able to demonstrate that you get improved forecasts with these high resolution data. And when we get real geohyperspectral instruments all around the globe, we're going to get phenomenal, much greater accuracy global forecasts as well. We've demonstrated through looking at stability, in this case, what's called the significant tornado parameter, which is generated from the wind field and the temperature field and the moisture field that you forecast with the model. We can predict then this significant tornado parameter, which tells you where severe thunderstorms and tornadoes will occur. And so these color diagrams over here are just showing this significant tornado parameter. And you see, this is for a storm that occurred in Nashville, Tennessee, just last year. And you can see the forecast, the 4-hour forecast, 5-hour forecast, and 6-hour forecast with satellite data all showed very high STP right where a tornado formed, which is right here at Nashville, Tennessee. And you can see it's right where the satellite data assimilated forecast predicted that it would occur. Whereas the operational forecast, which did not include the satellite data, this is the rapid refresh model, the high resolution model that NOAA runs, also predicted high STP, but not where the storm occurred. It was much further west. It's not near as accurate as with the satellite data. And in any event, even the forecasts not only predict where these storms will form, but even at what time they'll form. From all the forecasts that were conducted, all the forecasts, 5 forecasts ranging from 1 hour to 6 hours, predicted the highest STP at Nashville at the time the storm actually occurred, which is about 700 UTC time at Nashville. In any event, we've also, just to end up here, we've combined polar data with geostationary data over Asia. The polar hyperspectral with AHI, which is on the Himawari satellite. And we've also combined it with the GEARS data, the geohyperspectral data, and with AHI. And we've put all 3 instruments together too. The polar hyperspectral, the geohyperspectral, plus the geo multispectral, the AHI, to give us forecasts of, and we've shown that this is a case over China. Here you are, here in Taiwan, and but there is on March 3rd of last year, or 2 years ago, this was, sorry, 2 years ago, there was a, oh, I shouldn't touch anything, but 2 years ago, there was a very severe precipitation event in Southeast China. And so we used these data to forecast that event. And you can see here how adding the AHI to the gears, this is gears all by itself, but it's kind of choppy because the resolution is not so good with gears. It's 16 kilometers. Whereas if you use the 2 kilometer AHI and fuse it with gears, then you get much more detail. And this is showing analyses of 500 millibar relative humidity every 2 hours. And you see the continuity of this high humidity associated with this precipitation event. And finally, we were able to quantitatively validate these forecasts. In this case, we're looking at 3-hour precipitation accumulation in a 27-hour forecast, which were conducted with the China's operational forecast system, the GRAPES. The forecasts using our model without the satellite data, which is the control forecast, no sat. So these both don't have satellite soundings in them. And these are the 3 satellite forecasts. This being the gears plus AHI, this being the polar hyperspectral plus AHI, and this is all 3 instruments together. And you can see that the precipitation forecast is much better just visually with the satellite data, because without the satellite data, you don't see this gap that exists between these precipitation areas. But with the satellite data, you get some good evidence that there is a break in between 2 systems, 2 heavy precipitation systems for this case. So the satellite sounding data improves the no satellite forecast. And if you look at comparisons of these forecasts with the rain gauge and radar data, then you can compute skill scores and false alarm rates and so on that are used to validate precipitation skill and accuracy. And what you see is the satellite forecast has the lowest false alarm rate, which is what you want. And without the satellite data, you have lots of false alarms. You're predicting precipitation where it's not occurring, where it's much lower when you use the satellite data. And other skill scores, such as the probability of detection and what's called the critical success index. These are indices which relate to the number of correct forecasts over the total number of forecasts. And you want this to be very high, and it is for the satellite forecast, which are these purple, green, and cyan curves here, and very low for the non-satellite forecast, the GRAPES model and the control model. And so it clearly shows that the satellite data improves precipitation forecast significantly. And we see this over the US from our operational system as well. So in any event, I'll conclude here so we have some time for question. And just by saying that over the last 52 years since we launched the NIMBUS 3 satellite with those very first satellite sounding instruments on it, we have, greatly advanced, at least in our sounding capability. And unfortunately, the numerical modeling centers are still not using the data properly in the sense of using all the information that's provided. They tend to use just a small subset of spectral channels and assimilate radiances rather than retrievals, which are based on all the spectral channels, as I was showing earlier. But once they start doing that, then they're going to see even much greater improvements in their forecasts. They already see improvements with the forecast with the hyperspectral data, but not as much as they will see if they used all the spectral channels. And once we get these get these hyperspectral instruments on geostationary satellites all around the globe, what we call the global ring, which will consist of European, Asian, and US geostationary satellites. Then we're going to even see a revolutionary advance in both global and regional numerical weather prediction. So there's a lot of good things to come. It's an exciting future here, and I'm trying to hang around to share in that excitement as this evolves over the next 10 or 15 years. We'll see. But anyways, thank you very much for your attention, and I think we have 10 minutes or so at least for some questions. Thank you.
Thanks, Bill. Also know Chinese very well.
No, not too well. Let me see if I can get rid of this so I can see you guys. Yeah, okay, now I can see.
Okay, thanks, Bill. Yeah, I can anticipate that's the very powerful tool. Yeah, data and valuable information, not only from radiance, but also retrieved product level in level 2B and to be analyzed for nowcast to assimilate into model for the forecast. I think that's operational center. They have their concern, such as computation resources and data latency in time and so on. So probably there are several issues they need to solve before really use hyperspectral infrared sounder data. But that's all solvable, not tough things, as long as we have enough computation resources. Okay.
Yes. Yes. And you have the satellite right there in Taiwan. You have a direct broadcast readout system there in Taipei, I think. So you can get the real-time polar hyperspectral data, and of course you can receive the AHI data, I know, and probably data from the FY3 and the FY4 satellites as well.
Well, yeah, to be honest, I try very hard locally, try to let the operational center to use sounding data, but seems they are kind of late response on my request. We do our own, such like the data quality control and cloud clearing, or how to handling the cloud things by research mode. Yeah, that's also proposed by Jun Lee and I 2015. But I try very hard to let them know, because cloud is a lot. We have a lot of cloud coverage in our region, so that's the thing we need to solve at this moment.
Yeah.
Well, still, yeah. I'll try.
Yeah, I just want to say that regarding clouds, we're now, if you go to our website, I didn't give you the address, but you'll see that we are now also fusing the microwave data with the hyperspectral infrared to get soundings below clouds. That works as well.
Yeah. Okay. All right. Let me say, yeah. Question from audience.
Okay. Any questions?
Can you say something about the reason why the biases are greater in the upper atmosphere? Yeah, Hongrui from Colorado. Hongrui, there's one attendance from Colorado.
Oh, really? Okay. Well, the biases, you mean the differences between the radiance observations and those computed from the model? Why they're larger? It's probably because the model's wrong, not the radiances.
Got like your answer.
Yeah, the radiances are very accurate. They are very accurate. They're on the order of, at worst, 0.25 of a degree in brightness temperature. The CRIS instrument is 0.05 degree in temperature, even in the upper atmosphere. But the models can't predict the temperatures up there all that well. So, and we've seen this by GPS data, which it does measure the lower stratosphere quite accurately, that there's also big biases, were big biases between the GPS and the model data. But it's the model that's causing those biases, not the not the satellite measurements.
So the radius is correct. The retrieval is no problem. The problem is model for reference.
That's right.
Like
You have to believe the data. This is true with water vapor in particular.
Hello.
A lot of discrepancies between the model and water vapor radiances, and so modelers tend not to use the water vapor radiances, and they're missing all the important information coming from the satellite. The water vapor radiances are very accurate. They're the best measurement of water vapor that we probably have. Anyways,
okay. I'll quote your sentence to kick those operational centers say, we are the truth.
They say, yeah.
Hello. Hi. Thank you for the explanation. I think I have a question about the comparison between the wind field retrievals from the satellites and that with radio sound.
Yeah.
I think the biases between the two observational wind fields are greater in the upper atmosphere. I wonder why is that?
That's because the primary forcing variable of the model, the dynamics, is the water vapor, and it's the water vapor sounding, and the water vapor sounding, we lose sensitivity once we get into the high troposphere. Of course, we have very small number of water vapor molecules to emit radiation to space, so we lose water vapor sensitivity in the upper troposphere and stratosphere, and that's why the accuracy decreases in the winds at the high levels, is because the water vapor sensitivity is very, very low there.
Great, thank you so much. That clarifies a lot. Thanks.
Okay.
I want to ask question about the accuracy, the fusing in detect heavy rainfall compare with another products precipitation multispectral like GPM and GSMAP.
Yes. Well, we haven't actually compared with those sensors, so I can't give you a definite answer, but we need to do that. We need to. We think our assimilated data, which is, includes all the conventional data as well as the satellite sounding observations and a high resolution model, which puts it all together. And so after the product that we get by assimilating these data, all these data, the conventional data plus the high resolution satellite soundings, plus the very high resolution model that we're using, is able to diagnose the temperature, moisture, and wind field quite accurately, and as you would hope it would. And but we haven't done. We've only really validated against Raywin sounds, and in the case of storms, of course, we have surface reports and so on where they occur, provided by the Storm Prediction Center, so we can validate that. We validate precipitation using what you probably know as the Stage 4 precipitation product that NOAA puts out. So those are the quantitative validations that we have. We haven't really compared with GPM or other sensors. That would be a good thing for a student to do for a thesis, a master's thesis anyway. I'll have to. That's a good idea. I'll get a student to do that.
Thank you.
Thank you for your presentation. And I really I don't really catch the concept about how to combine the hyperspectral data with the geostationary data like ABI.
Yeah, what we do, it's a fusion process where we take the ABI data, and we always have ABI data where we have the polar data, because it's nearly continuous over large areas. And so we can take the ABI data and average it to the polar data fields of view. Okay, so we have what we call low resolution ABI data, which is the ABI data at the polar satellite resolution. And then we have, of course, the full resolution ABI data. So we can relate then the low resolution ABI data, where we also have the polar hyperspectral data. We can relate that to the high resolution data. And we have a fusion scheme. We use a system that's called KD tree searching, where it finds the soundings, the low resolution soundings, which are the best match to the high resolution ABI data. And then it takes the polar soundings that go with that low resolution ABI data and averages them in a weighted way to get a prediction then of the hyperspectral sounding for the full resolution ABI data. And it's quite accurate if you're not too far away in space and time. So we make sure that our polar data is within 55 kilometers of the ABI data that we're fusing it to. And we also make sure it's within 3 hours of time of the ABI data. If you get any further away in space and time, then it doesn't work very accurately. And it shows that we really need a true geo-hyperspectral instrument to get what we want. But for a large region, and much of the time, this fusion technique works quite well. And I can, if you look at my paper that you have the reference for it, the JTech paper, it gives you references and describes also how this fusion technique works. I suggest you look at that paper.
Okay, thank you very much.
Or if you email me, I will send you the paper.
Okay.
Thank you.
If you have questions or comments, you can email to Bill.
Yes.
If you don't know his email address, and you can ask me as well. And
yeah, well, please give everyone my email address so they can email me if they have questions or want papers or anything like that. I'll be glad to send them to you.
Okay, sure. No, definitely no problem. I will forward your email to them.
Okay.
All right.
And thank you for allowing me to participate in your seminar series.
Okay, thanks. Takes a lot of your time and especially your family time. Thank you.
Okay.
Hope you stay healthy and good.
Okay, 谢谢.
谢谢. Okay, thanks.
再见.
Bye.